Hello everyone and welcome to this section on logistic regression. In this lecture, we're going to describe the theory behind logistic regression, as well as the theory behind classification metrics in general. Not all labels are continuous. Sometimes what you need to do is predict categories, and this is known as classification. Logistic regression is one of the basic ways to perform classification, and don't be confused by the word regression. Even though logistic regression has that word in it, it is a classification algorithm. If you want some theory behind the mathematics of logistic regression, go ahead and read sections 4 through 4.3 of an Introduction to Statistical Learning by Gareth James. If you want to fully understand some of the concepts behind the evaluation methods and metrics behind classification, I really recommend that reading assignment. Alright, so we want to learn about logistic regression as a method for classification. And some examples of classification problems are things like separating spam emails versus ham or good emails, trying to decide whether a customer is going to default on their loan, or even diagnosing a disease, for instance if someone has cancer or not. And all of those above examples are examples of what's known as binary classification, where the classification is just between two classes. And so far we've only seen regression problems where we're trying to predict a continuous value. Although the name may be confusing at first, logistic regression allows us to solve classification problems, where we are trying to predict discrete categories. The convention for binary classification is to have two classes at 0 and 1, and we're going to walk through the basic idea of logistic regression. We'll also explain why it has the term regression in it, even though it's used for classification. Imagine we plotted out some categorical data against one of its features. So on the x-axis we have some representative feature that goes from -10 all the way to 10. And the y-axis represents the probability of belonging to class 1. So you can see here the blue points belong to class 0, which means they have 0 probability of belonging to class 1. And the orange points on top belong to class 1, so they have 1 or 100% probability. Now we can't use a normal linear regression model on binary groups. It won't lead to a good fit. You can see here that we just don't fit to many of the points. We need a function that will fit binary categorical data. And it would be great if we could find the function with this sort of behavior. Something like this tries its best to match up to the different sides of the y-axis. Luckily for us, there is such a function. The sigmoid, also known as the logistic function, takes in any value and then outputs it to be between 0 and 1. And you can actually see the formula there on top of this graph. And when you plot it out, this is what it looks like. And this basically means that no matter what value of z you put into this function, the output will always be between the numbers 0 and 1. And this means we can take our linear regression solution and place it into the sigmoid function, or the logistic function. So what does this actually look like? Well, basically we have our old linear model, something that looks like y plus beta 1 times x, and we insert it into the sigmoid function, that 1 over 1 plus e to the minus, and then that's where our linear model goes. Which means no matter what we put into that linear model as an output, once it goes into the sigmoid function, the value will always be between 0 and 1. And the result in a probability from 0 to 1 belonging to the 1 class. And then we can set a cutoff point at 0.5, so that anything below it results in class 0, and anything above it is class 1. We use the logistic function to output a value ranging from 0 to 1, and then based off this probability, we can assign it a class. After you train a logistic regression model on some training data, you will evaluate your model's performance on some test data, and you can use a confusion matrix to evaluate classification models. So let's discuss that in a little more detail. So this is what a confusion matrix looks like. It's basically a cross diagram between the predicted condition, or what you predicted the label to be, versus the true condition, what the true label actually was. So you can see this cross diagram, we get various outputs, and let's go through the four main ones here. If our true condition was that the condition was positive, for example, we were testing for a disease, and true condition is that the person really did have the disease. And the predicted condition, what our model ended up outputting, was that this person does have the disease as our prediction. Then we have what is known as a true positive, which means the person does have the disease, or the condition was positive, and our prediction was that the person was positive for this disease. So that's a true positive value. Now let's imagine that the true condition was actually false. So this person doesn't actually have the disease. However, we predicted for it to be positive. This means we have a false positive, also known as a type 1 error. If we look on the other column, the prediction negative, we have the opposite set of values. For example, if the person truly has the disease, but we predict that they do not have the disease, we have what's known as a false negative, or a type 2 error. Likewise, if the predicted condition is negative and the person is truly negative, so the condition is negative, then we have what's known as a true negative. And we can expand this matrix with ratios, and these ratios are essentially all the evaluation metrics we talk about when discussing classification. So some of the more common ones are things like accuracy. So you can see all the way on the left-hand side at the bottom of that column we have accuracy. And accuracy is the sum of the number of true positives plus the number of true negatives divided by the total population, which basically means how many did you get right out of the total population. Now, in certain cases, that's not enough information. You also want to know things like the number of true positives divided by the number of conditional positives. So that can be something like sensitivity or recall, otherwise known as the true positive rate. Then there's other things like precision, which is going to be the sum of the number of true positives divided by the prediction positive. So all of these metrics can be available to you. The main idea is that they're all ratios based off of counts divided by some sort of total population or some sort of total condition negative or total prediction positive, prediction negative, etc. So you don't need to memorize any of these. In fact, this is just from the Wikipedia page, so you can always reference it. All you have to be aware of is that the confusion matrix can lead to all these various metrics. Again, the main point to remember with the confusion matrix and the various calculated metrics is that they are all fundamentally ways of comparing the predicted values versus the true values. The question of what constitutes a good metric will really depend on the specific situation. In some cases, accuracy is really important. In other cases, things like precision and recall are really important. It really depends on the specific situation. So asking the question, hey, is this a good recall value or is this a good accuracy value, will really depend on the cost associated with each of those metrics. So let's walk through an example of how we could use a confusion matrix to evaluate our model. And we're going to touch back again on the example of testing for a disease, since that's one of the most common examples whenever we're discussing a confusion matrix. So here we have our confusion matrix, and we tested a total of 165 people, or n equal to 65. And all the way on the left-hand side, we can see the actual truth, whether or not this person has the disease, yes or no. And on the columns, we can see what we predicted, no or yes. So, for example, the test for the presence of the disease, no is equal to a negative test, which is equal to false, or 0. And yes is equal to a positive test, or true, is equal to 1. So again, the basic terminology can be things like true positives. In this case, that's equal to 100, actual yes and predicted yes. True negatives, in this case, equal to 50, actual no and predicted no. And then we have our false positives and false negatives. So false negatives is 5, where the actual was yes, but we predicted no, so a false negative. And then false positives is equal to 10, where the actual was no, but we predicted yes. So the accuracy answers the question, overall, how often is it correct? And we get that by summing the number of true positives versus the number of true negatives over the total. And in this case, we get 91% accuracy. The misclassification rate, or error rate, answers the question, overall, how often is it wrong? And you can do something like take the number of false positives plus the number of false negatives over the total. And that gives you a rate of around 9%. So if you ever get confused on the discussion between type 1 errors or type 2 errors, aka false positives versus false negatives, this is a little handy, funny picture for you to remember. So telling a man you're pregnant, well, that's definitely a false positive, versus telling a woman who's obviously pregnant you're not pregnant, that's a false negative, aka type 1 error versus type 2 errors. If you're still confused on the confusion matrix, no pun intended, that's really no problem. What I would suggest you do is check out the Wikipedia page for it. That's where all the diagrams are from, and it actually has a really good diagram with all the formulas for all the metrics. And essentially what you're going to do is just refer to those in case you ever want clarification on them. And throughout the course, what we're usually going to do is just print out one of the metrics, such as accuracy or recall. Now, binary classification, which is what we've been discussing, has some of its own special classification metrics, and these usually include visualizations of metrics from the confusion matrix. The receiver operator curve, or ROC curve, was developed during World War II to help analyze radar data. So let's take a look at the ROC curve. The ROC curve is just a plot of the sensitivity versus 1 minus the specificity, otherwise known as the true positive rate on that y-axis plotted against the false positive rate. And if you want a general outline of what the ROC curve looks like and how it can be evaluated, this diagonal line across the center in a red dashed line is essentially what a random guess is. Basically a 50-50 chance of getting it right. If you're above that line, that means your model is performing better than a random guess. If you're below that line, that means your model is performing worse than a random guess. And if you have absolute perfect classification, then your model is eventually going to reach 1 over there. And that's what your curve will look like, basically right up against that y-axis. So a full discussion of the ROC curve is beyond the scope of this course, but if you're really interested in it, the reading assignment goes into much more detail. For now, you just need to know that the area under the curve is a metric for how well a model fit the data, with 1 being absolutely perfect fit. Alright, let's continue on exploring these concepts with a walkthrough of the documentation example, and then we'll also add some more stuff on evaluation to the example. Thanks, and I'll see you at the next lecture.